Y'all, let's get started. Just to remind you, I said this in class, but you have 28 questions. There'll be 8 free response at the beginning. Like I was telling somebody earlier, the free response, they're really questions that you would have had as multiple choice. It's not like they're special questions. Often you'll find multiple choice questions that are a lot like the free response. So as you practice through the old exams, you can look for these types of questions. That they'll be similar to what you'll see for the free response. The only difference is you can get half credit for the free response, and you don't have answers to choose from. So you have 28 total. And of those, the free response, you're going to have 4 separate questions with 2 parts each. The first one will be a torques. The second one will be momentum, conservation momentum. The third one is Archimedes Principle. And then the fourth one is the equation of continuity. That's the A1V1 equals A2V2 and Bernoulli's principle. I'll ask you, what is the speed in the new pipe and what is the pressure in the new pipe? We've done that, so no surprises. That's what it'll be. And then you'll have 20 multiple choice questions. They're all from chapters, 8 and 9, roughly about half and half. 20 questions. So look at the old exams, look at the notes, look at the questions we did in class, look at the concept tests. I posted those a day or two ago. Both 8 and 9 are on there. What do you want to look at? Pressure problems? Yeah, let's pull up some old exams and we'll see. I think y'all have 15 in your book. Let's go to a little older. Let's go to 14. Usually I stick to the 2-column exams. So if you're looking back at old exams, if you get to a note where there aren't 2 columns, those might still be useful for you to look at, but you're going to begin to see sort of different types of problems just because the way I wrote exams was different. Y'all understand what I'm saying? Like if you go back and you see, I think, what's that? Yeah, like this. There's still good questions there for you to try out, but just be aware you might see different things too. Anyway, so fluid problems. We had lots of different things with fluids. Right, we had Pascal's principle, which you'll have one of those, something like this. We had Bernoulli's principle, that's with the velocity goes up, the pressure goes down, the conservation of energy for fluids. We had equation of continuity. That's when you have a pipe that gets narrower or wider. It changes the velocity of the fluid flow. And then we also had pressure measurements, like the manometer and the barometer. You need to know all those. You're going to have problems with all those. Any of these stand out to y'all that y'all want to look at in particular? 22? Okay. So 22 is our manometer problem. And here I want to know, what is the height of this column when the pressure P is 0.2 atmospheres? First of all, make sure that you're quick at converting atmospheres to pascals, because you'll have to do that most likely. And it's easy. 0.2 atmospheres is just 0.2 times 10 to the 5th pascals. I just add that times 10 to the 5th. I want to know that the height here, I know that the pressure is equal to P naught plus rho GH. Usually it's plus or minus, but it doesn't really matter here because P naught is equal to 0. And so the plus or minus sort of becomes moot because P is just going to be equal to the rho times G times H. By the way, I know that if pressure is 1 atmosphere, then the height of the column is 760 millimeters. Oh no, this is water. I'm sorry. If it's 1 atmosphere, the height of the column, do you remember for water, if I'm at 1 atmosphere, what's the maximum height? 10 meters, 10.3 or 4, I think. So I know that this one has to be less than 10 meters, so I can get rid of this one and this one. In fact, I could probably get rid of this one, most likely, but I'm not absolutely certain. So let's keep that for now. And now I can time P is equal to the density times G times H. That's 1,000 kilograms per cubic meter. Just as an aside, remember for water that for water the density is 1,000. It's also 1 gram per cubic centimeter. That means for every milliliter of water, a milliliter is a cubic centimeter. For every milliliter of water, that's 1 gram of mass. It's just sort of a useful number to know. Anyway, the density is 1,000 kilograms per cubic meter times 10 times h, and this is 0.2 times 10 to the 5th. And then if I solve that for h, that is going to be 2 meters. I just divide 0.2 times 10 to the 5th by 10,000, and it gives me 2. Okay? A similar type of problem is where I have 2 non-zero pressures, and that's sort of like over here in number 26. And number 22, this is a particular type of problem. It's called a barometer. And a barometer is just when this pressure is 0. That's really the only thing. Over here, this is a manometer. And a barometer is just a special case of a manometer. A manometer has 2 pressures, each of which are non-zero. And the only difference in this is that I have to consider this plus or minus. If P is bigger than P naught, then I use the plus. If P is smaller than P naught, then I use the minus. And so here, which one's the bigger of these 2 pressures? P or P naught? P naught is bigger, right? Because it's pushing this fluid down, it's pushing it up into the column. So for this one, since P naught is bigger than P, I would use plus or minus in this equation. I'd use minus, right? Because P is smaller than P naught. So I have to subtract that rho GH term to make it smaller. And the answer to this question then would be that P is bigger than, oh, no, sorry. C. Okay. Probably going to have a manometer question or some sort of measurement question. This idea that pressure is rho GH, remember that comes about, we defined this early on, that if I have a point in a liquid that's at a height, that pressure at that point is equal to that rho times G times H, plus whatever pressure there is at the top pushing down. Okay? So you could see that too, just at a certain depth in a liquid, what is the pressure at that point? We've done that a number of times, and you'll see it in the old test. Okay? Let's just sort of scroll through. Can I clear this, y'all? All right. Here's equation of continuity. Let's just sort of do this. You're going to see this early on. This is free response. And then I will also ask you what is the pressure in the second pipe. Like I would give you P1, whatever it is, and then I would ask you what is the pressure in the second pipe. So I have 3 meters per second through an area of 0.5 square meters. So my pipe looks something like this. I have 3 meters per second here. I want to know what is V here. My area over here is 0.5 meters squared, and over here it's 1 square meter. So my area doubles when I go from one pipe to the other. So what's going to happen to my speed? Is it going to go up or down, first of all? It's going to go down, right? So it has to travel faster through the smaller pipe just to get the same volume flow rate, to get the same volume of fluid moving at the same amount of time. And over here, it has a much larger space to move through, so it can move slower. So I know it has to be slower than 3 meters per second, and I know it has to be slower by a factor of 2. So the answer is going to be 1.5. If you didn't see that, let me show you how that works. So I do A1V1 equals A2V2. A1 is 0.5 square meters. V1 is 3 meters per second. A2 is 1. And so V2 is equal to 0.5 times 3, or 1.5. Okay? I thought about it in the terms of, well, my area increases by a factor of 2, so my velocity has to decrease by a factor of 2. It was 3 here, now it has to be 1.5. You'll have an additional question on the free response where I ask you, what is the pressure here? I'll give you this pressure. Let's just sort of make up some numbers. Let's say that it's, I don't know, 80 kilopascals. All right, and I want to know what is P2. You would set it up like this. You would say 1/2 ρ1 V1 squared plus P1 is equal to 1/2 ρ2 V2 squared plus P2. Remember, this is the conservation of energy for fluids, for fluid flow. The energy per unit volume is conserved. I have all the values here. 1/2 of 1,000, assuming it's water. I think it is. Yeah, it's water. Times V1, which is 3 meters per second squared, plus P1 is 80,000 pascals, or kilopascals, 1,000 pascals, is equal to 1/2 of ρ2, which is 1,000. Be careful, those rows don't cancel out, right? Because there's not rho in every term. So don't try to cancel them. Some of you I know will try to do that just because you're in the heat of the exam. And then the V2 we now know is 1.5 meters per second. That's what we had up here, plus P2. And then I'd solve that for P2. I'm not going to do that here. I'd have to get at my calculator. But you could solve that for P2. You add these two terms and then you subtract that term to find the pressure. Is the pressure going to go up or down? It's 80 kilopascals, and this side, what is it over here? More or less? More. It's going to be more. Very good. So if the speed goes up, the pressure goes, or excuse me. Yeah, if the speed goes down, the pressure goes up. There's an inverse relationship between pressure and velocity, according to Bernoulli's principle. Because this whole thing has to be constant. So if this term goes up, that term goes down. That'll help you find the answer too, although this is a free response, so there are no answers provided to you. All right. Let's do number 25. This is like another of your free response. Archimedes Principle, man. People just get confused with Archimedes Principle. Is that true? Are y'all confused by it? Not y'all, because y'all are awesome. But like most normal people are confused by Archimedes Principle. So a ping pong ball has an average density of 84 kilograms per cubic meter and a volume of 3 times 10 to the 5th. The ball is completely submerged. What is the buoyant force acting on it? All right, you have some extra information that you don't need here, but we're going to add to this, and you will need it. My buoyant force is equal to rho times V times G. Rho is the density of the fluid. So be careful. Don't use the density of the ping pong ball. Like that wouldn't be right. It's the density of the fluid, which is going to be 1,000. Volume is the volume of the object, which I'm given. That's the volume of the ping pong ball, and then G. So it's going to be 1,000 kilograms per cubic meter. V is 3 times 10 to the minus 5 cubic meters, and then G is 10. What is that? 0.3, I think. Is it D? Is D 0.3? Okay, yeah, so it's 0.3. That's my buoyant force. So the question that you're going to have is going to be a little bit similar, but a little bit more complicated. In order to have this ping pong ball submerged, that means that you have to be pushing it down. Like, you ever been in the swimming pool and you have a beach ball and you push it down underneath the water? Have y'all ever done that? And then you let it go and it flies up? Have y'all done that? Everybody? That's fun, right? So I want to know, what is that force that you have to push down on in order to make this thing submerged? I'm going to draw it a little bit differently so it'll look more like our, oh, I can't do that. So it'll look more like our free body diagrams. So here's the force. That's the force you have to push down. There's also a force weight that's acting downward on that, and then there's a buoyant force. So I have those three forces that are at work. I already know what the buoyant force is. I calculated it. in order to find F, I need to sum up all my forces. It's going to be FB minus FW minus F, and that's equal to 0. So F, if I want to know what force is required to push that beach ball down under the water, is going to be equal to the difference between FB and FW. Okay, so FB is 0.3 newtons minus the weight. Oh, shoot. So how do I find the weight of this object? Well, weight is equal to m times g, but I don't know the mass. And so you're probably going to encounter a question, I don't know if it's the free response, where you just don't seem to have the information that you need. But I can find the mass of this object fairly simply, right? Because look, I have the volume and the density. So don't freak out. You'll have the information. It might not be stated in the problem, but you'll have the density on the equation sheet. And so if you have the volume, you can find the mass. So remember, density is mass over volume. I'm looking for the mass, so that's density times volume, which is 84 kilograms per cubic meter. That's in the problem. But as I told you, on the test, I will not give any constants in the problems. They'll all be on your table. And so 84 times 3 times 10 to the minus 5. I get 0.0025. That's in kilograms. And so the weight is going to be 0.025 newtons. I just multiplied that times 10. So I get 0.3 minus 0.025. So what's that? 0.275 newtons. That's the force required to submerge that ping pong ball. That's a free response question. Okay? 100%. I want everybody, especially those in this room, everybody to get that right. And you will, right? Yeah. Those are supposed to be gimme questions. They're gimmes, right? Yes. Come on. Say yes. Thank you. Do you want to do another angular momentum problem? Let's do one. This is another free response. So you'll see other questions like this. So calculating angular momentum, calculating moment of inertia. But on the free response, I'll combine several different things. I'll have two shapes. I don't know, let's say it's a hoop plus, I don't know, what do you want to do? A hoop and a bar. And they're spinning and they come together. And I want to know what is their new speed. So let's say that, gosh, is this how I did it? No, I'm sorry. There was a problem like that where I asked you what is their combined moment of inertia, but on the free response it was more like this. I have some object that changes shape. That is, it changes its radius, or it changes its radius, and that changes its moment of inertia. So let's say that I have a bar, for example. It could be a hoop. I don't really remember what it is. But let's say that I have a bar that is 2 kilograms and 2 meters long. And it gets shorter, keeps the same mass, but it gets shorter, say by a half. The moment of inertia now is going to change, right? Because I have 1/12 mb squared, 1/12 of 2 kilograms, 2 meters squared, and that's equal to 8/12, or 2/3. Is that right? Yeah, 2/3 kilogram meter squared. But over here, my moment of inertia is equal to 1/12 of 2 times 1 squared, so 1/6 kilogram meter squared. My point is that my moment of inertia has changed. It's like the figure skater pulling her arms in, right? And so if this thing is spinning initially, if the moment of inertia goes down like it is, then that means the speed is gonna go up, right? So I can calculate that new speed. Let's say that this thing is spinning at a rate of 4 radians per second. And I want to know now what is the rate at which this other object is spinning. So I'd say Li equals Lf. I have I initial, omega initial equals I final, omega final. That's going to be 2/3 kilogram meter squared times omega initial 4 radians per second is equal to 1/6 kilogram meter squared times omega final. And then you can solve this for omega final. Going to be going faster or slower? Faster or slower? Pulling your arms in. What do you do? Go faster, right. So you pull your arm, you spin faster. That's what they do. When you lower your moment of inertia, if I lower this value, which is what I've done, this value is going to go up, inversely related. If one goes down, the other goes up, and vice versa. So she's going to be going faster. This bar will spin faster. Which situation will have more energy? The first situation, big moment of inertia, small rate of rotation, or small moment of inertia, big rate of rotation. Which has more energy? Rotational kinetic energy. The faster one, right. Very good. That's going to come up in at least 2 problems that I can think of, maybe more. So remember, kinetic energy is 1/2 I omega squared. So if I increase omega by a certain amount, that has a bigger impact than if I decrease I by the same amount. So the faster, which is the final state, will have more energy. One of your questions is going to be, what work is done in order to change the energy of that rotating object? What is the amount of work that has been done? How do I find the amount of work that's done? You find what? Yeah, not just the rotational kinetic energy. It's very close. The change in kinetic energy, right? So to find the amount of work that's done, I'm not going to work it out, but we did this in class. To find the work that's done is the change in kinetic energy, which is going to be Ke final minus Ke initial. That'll be one of your questions. I wasn't going to tell you that today, but then I changed my mind. Okay? I know, such a nice guy. No, not really. I'm kind of a jerk sometimes. But that's how you find the work, is just the change in kinetic energy. Chapter 5, right? The work energy theorem. That if I do work on an object, I change its energy. That's page number 1. Okay? And then I think we've done those torque problems over and over. Y'all cool on the torque problems? Okay, let's look at some other stuff. Yeah, Victoria.
Number 9 from exam 218.
Mm-hmm.
There's one with the figure skater.
Okay, yeah, so you often see questions like this, right? Figure skater pulls her arms in to decrease her moment of inertia by a factor of 2. And as a result, she spins twice as fast. And the reason that is that her angular momentum is constant, right? So if I increase my moment of, or if I decrease this by a factor of 2, that is, I divide it by 2, that means that this is going to increase by a factor of 2. But this is asking about her rotational energy. What has happened to her rotational energy? Now, you've already said that if something is spinning faster, it has more, or if I change the moment of inertia to make it spin faster, that makes its rotational energy go up, just like the previous problem. So if I have my moment of inertia I double my speed, what happens to the kinetic energy? Well, let's say I doubled this, and I halved this. So I have a change in my kinetic energy. I have to do the same to this side. A half and the 4, that's 2 squared. So that's where the 4 comes from. That means that I'm going to double my kinetic energy. So my rotational kinetic energy has increased by a factor of 2. Okay? Is that good? You get that right tomorrow? Sure? Okay. Okay? Sorry, something was on my mind. I forgot what it was. Okay, what else I want to look at? Huh? 18? Yeah, so your problem on the free response will be a lot like number 18. Okay, I'll try to keep the torques fairly simple, kind of like this one has a simple torque on it, right? I think I gave you 2 forces that produce a torque, so you have to add or subtract them and figure out what that is, but I tried to make them as simple as possible.
So the free response will be like 18 or 19.
That's right, yeah. Oh, well, 19 is different, but yeah, it would be something like that, like I would ask 2 questions about it. Yeah, of course, yeah. All right, so there are several steps, though, that you have to follow in this. The first thing you want to do is find, well, you can find the moment of inertia first. I know for a hoop that I is equal to mr squared. That's on your equation sheet. It's in that table. By the way, tomorrow you'll get a whole separate equation. You'll get a whole separate equation sheet. You can tear it off of your exam and sort of keep it wherever you need to keep it. And then you'll have your bubble form with your free response on the back of it, just like usual. But the equations won't be on the bubble sheet. Anyway, mr squared, the mass is 2, the radius is 1, so that's 2 times 1 squared, that's equal to 2. So then I need to find my net torque. This one's easy because there's only one force. That's 30 newtons times 1 meter. So it's 30 newton meters. And then here I need to find the angular acceleration. So the net torque is equal to I times alpha. That's on your equation sheet. But remember, it's just F equals ma. Torque is like our force. I is like our mass. Alpha is like our acceleration. So 30 equals 2 times alpha. So alpha has to be 15. And then I could ask you any number of questions like, what is omega after a certain amount of time? Or what is the kinetic energy after a certain amount of time? If you wanted to find omega, you would say omega is omega naught plus alpha t. We'll assume that it's at rest, so that means this is 0. So it's just going to be 15 radians per second squared. That's this quantity times t. I don't know, we'll just say t is equal to 3 seconds or whatever. So that would be 45 radians per second. You're going to have a problem where you have to find the total kinetic energy. We did one like this. Remember what I'm talking about? Where I have some object that's rotating or rolling, and it has both translational kinetic energy and rotational kinetic energy. In the course of that, you usually have to either figure out V or figure out omega. Don't forget that your quantities V and omega are related. Well, let's imagine. We say we have a hoop and say it's rolling in this direction. Let's say V is 2 meters per second. We'll say the radius is 3 meters and the mass is 2 kilograms. And I would ask you, what is the total energy? Y'all could do that, right? Yeah. So I'd say 1/2 mv squared. I have 2 parts to the energy. 1/2 mv squared, that's the translational energy. That's 1/2 of 2 kilograms times 2 meters per second squared. It's equal to 4 joules. And then the other energy this is where it gets a little bit trickier, is 1/2 I omega squared. And I have to figure out what is I, and I have to figure out what is omega. But I know I for a hoop is mr squared. So that's 2 times 3 squared, 18. And then I also know that omega is equal to V over R. That's on your equation sheet. The equation is V equals omega R, and I just solved for omega. And so omega is equal to V over R. That's 2 meters per second divided by R, which is 3 meters. So that's 2/3 radians per second. Then I can find my kinetic energy. Be 1/2 of 18 times 2/3 squared. What's that? 4, I think. I think that's 4. So the total would be 8 joules. I did that right? The 3 is squared, so I can say that. And then 2, yeah, it's 4. So I add this energy to this energy. They're identical here. They don't have to be identical. It depends on the shape that you have, the speed. Okay? Good on that? No, cool? Let's sort of peruse some of the other problems. You'll holler out. Okay, and these lift problems, once you know how to do these are fairly easy. It's just F over A equals F2 over A2. Whatever the increase in area is, your force is increased by the same amount. So here my area goes from 0.01 to 1 meter squared. It goes from 0.01 right here to 1 meter squared. So it has an increase of 100. That means that my force is also increased by 100. So if I have 100 newtons, then I'm going to have 10,000 newtons. Or you can just use this equation. F1 over A1 is F2 over A2 to solve for it. Yeah?
Is that a free response?
No, not a free response. But you'll probably see it on the multiple choice. So don't really think of the free response as being worth more. Really think of the free response as questions that I tell you are going to be on the test, and then you can have the opportunity to get half credit on them if you make a mess up. And you don't get that opportunity on the multiple choice, right? If you mess up, you just mess up. I don't even care. I just mark it wrong. But on the free response, I care. I care about you, and I want you to do well. But on the multiple choice, it's, every man for himself. Yeah. Okay, yeah, so be careful on that. As you're reading whether it's the mass or the weight. Whenever you're dealing with this, you need the forces. And so just, remember that my force is equal to my mass times g. So if I ever give you a mass, then just translate it back to a force. Just multiply it by 10. Read it carefully. I know I'm not meaning to be tricky. It's just, you just have to read. Every word's important, okay? That's not just my exam. That's everybody. That's life. Let's look at 25 here. So a cylindrical container is 4 meters tall and has a diameter of 2 meters, and it contains 200 kilograms of water, and the container is not full. What is the pressure exerted on the bottom by the container by the water? Okay, so this could happen in a couple different ways. In this case, the container is not full. So I have some amount of water that's inside of the container that has a mass of 200 kilograms. That means that I have a weight pushing down that is 2,000 newtons, pushing down onto that that area, and the area is a diameter of 2 meters, so that has an area of pi r squared. That's pi times 1 meter squared. The 1 meter is just half the diameter, half of 2, and so that's, we'll just call it 3 square meters. So I have a pressure equal to force over area, which is 2,000 newtons divided by 3 square meters. So it's going to be, was it 640? Is that right? Yeah, divided by 3.1. Yeah, 640. So that pressure would be 340. Notice, so if I had a cylinder that was all the way full, and let's say that the height was 4 meters here, I can find that pressure without even knowing how much is in, like what is the mass of the water. Because I can also find the pressure just from the height of the column. And that's equal to rho times g times h. So that would be 1,000 kilograms per cubic meter times 10 times the height h, which is 4 meters. And so that's going to be 10,000 times 4, 40,000 pascals. So if you don't know the mass of the water, if you just know the height of the column, then you can find the pressure. It doesn't matter about what is the diameter of it. It doesn't matter what is the mass of the liquid. That it's all really just the density and the height of the column. It's going to allow you to find that pressure. Notice here that this has 200 kilograms of water. That it's a tiny amount of water in this container. I mean, this is a big container. It's a container that's this far apart, or this wide, basically. So it's just going to fill just the very bottom part of that. Okay, y'all see the difference in those two problems? That one of them is finding the pressure by force over area, and one of them is finding the pressure just by the height of the column. You'll probably have to do both of those tomorrow, finding the pressure through both means, which you'll be able to do, right? Okay, what else? This is like one that we did earlier, number 21, with the Bernoulli's principle. Any other things that are burning? Questions? Just topics that you're having difficulty with? Yeah, Wendy? Which one was that? I forget what I worked. So I think I listed them here. Oh yeah, I thought I did one like that. Yeah, I think I did one. Do you want me to do it again? Okay. So the Bernoulli's one, right? That's what you're asking? But these are the free response. The torques, the conservation momentum, Archimedes Principle, and then the continuity equation of Bernoulli's Principle. That's the one where you have like a pipe that gets smaller with a 1/2 rho v1 squared. Can we do that one? Okay. Listen, y'all don't, many of you don't really understand the value of practice, because you say, oh, I got that down, and then you say, I can move on to something else. But when you're sitting in the test, like everything that you know just vanishes, right? You ever had that feeling? The more you practice, the less it will vanish from your memory. So practice is your friend. Even if you've done this problem, do it 3 more times, and it will help you to remember it more when you come to the exam. That you need to be better in the exam than you are when you're studying. Understand? You need to know it better during the exam than you do when you're studying. Because you're all alone in the exam. Nobody's there to help you. But when you're sitting out wherever you are, you have all sorts of helps. But all alone. It's a dark, dark place. No, it's a happy place. So I have a pipe let's give it some dimensions. We'll say the area over here is 4 square meters. We'll say this is 2 square meters. Let's say the speed here is 3 meters per second. And let's say that the pressure here, P1 I'll call it, is, I don't know, 70 kilopascals. And I'll ask you 2 questions. I'll ask you what is the speed in the second pipe, which many of you can probably just tell me right off. Can you tell me right off what the speed is? 6, right, 6. Because my area goes from 4 to 2, it decreases by 2, so this has to increase by 2. Okay, so my new speed is going to be 6. If you didn't get that, I'll show you. And then the second question I'll ask is what is the pressure in that second pipe? So 2 parts. Part A, what is the speed? A1 V1 equals A2 V2. A1 is 4 square meters. V1 is 3 meters per second. A2 is 2 square meters. And then V2. 12 divided by 2 for V2 is equal to 6 meters per second. It increases by a factor of 2. And then the other thing I'll ask is, what is the pressure in this pipe? Since it's speeding up, I know it has to be less than 70,000 pascals. It has to be a lower pressure. Bernoulli principle, 1/2 rho 1 V1 squared plus P1 . I remember in Bernoulli's principle, there is another term. It's the rho GH term. That's for the gravitational potential energy. But just to make the algebra easier, I never include it. But remember, this is kinetic energy. It sort of looks like kinetic energy, right? mv squared. This is work. And then there's also the potential energy term. So this is 1/2. If we're dealing with water, that's 1,000. V1 was 3 squared plus 70,000 pascals is equal to 1/2 of 1,000 times 6 squared. That's the velocity we found over here, plus P2. And so P2 is going to be 500 times 9. 500 times 36. I think that's right. Whatever that is. Did I do that right, y'all? Is that right? What's the answer? Y'all know? That doesn't matter. You can do that. So that would be the second question. Different numbers, same problem, different numbers. Okay? I'll do that, right? All right? Yeah.
We're going to have any questions asking about like the volume of the submerged part of objects.
Probably, yeah. But with those, let me just clarify this. If I have an object that is fully submerged, the buoyant force may or may not equal to the weight. You don't really know. Probably not equal to the weight. In fact, the buoyant force is probably less than the weight. It could be equal, but probably not. In fact, usually the buoyant force in this case is less than the weight. That's why it's not floating up at the top of the surface. But if I have an object that is floating, the buoyant force has to equal the weight. Right? And also remember, we had this in the clicker question. Remember the clicker question where we had 2 containers that were filled up to the brim with water? But one of the containers had one floating. Remember the difference in the masses? Which one had the bigger mass? The one with the floating object in it? Or the one that was just full of the liquid? Which is bigger in mass? They're the same. Yeah, I was trying to trick you because I didn't offer that as an option. These have the same mass because the buoyant force is acting on this thing is equal to the weight of the block. And remember, the buoyant force is equal to the displaced fluid. So when you put this block into the container, it displaced all this fluid, which was equal to its own weight. And so that's why these two have exactly the same weight. They're equal in mass or weight. Because the buoyant force is equal to the weight of a floating object. Not necessarily true if it's not floating. If it's submerged, it's not true. Okay? So a couple times I think that comes up, that idea. Yeah.
It's just in the second one, you said that the weight of the object is the same as the buoyant force.
Right.
So is that just only if it's halfway submerged?
If it's not fully submerged. It doesn't have to be halfway submerged, but just not fully submerged.
So like even if it's, I don't know, like how some things like sit on top of water.
Mm-hmm.
Is that the same thing?
I wouldn't give you that. Like it would either be submerged or not submerged.
Okay.
But yeah, you're right. When it's just sort of sitting at the level of the water, that means that the buoyant force is really, really close to the weight. Okay?
Will there be Young's force?
Yeah, I think so. Want to do one of those? Yeah, we haven't done any of those, have we? Really, those is just sort of knowing the equation and knowing what numbers to put in. They're all pretty much the same. Guess there wasn't one on that one. You're going to have to rank stuff. Make sure you're ready for that. Shapes. Did you just groan? Did somebody just groan? I find that my dad came to visit last week, and that man moans and groans more than any. Your parents moan and groan when they move around? But I feel like I do too now, because I go to the gym, and it takes me a lot longer to recover than it used to. Like if I go to the gym, it takes me 2 or 3 days. I feel like I'm sore for 2 or 3 days, and it used to be it was just a half a day, and I was back to normal. But that's why they moan and groan. Shoot, what am I looking for? Oh, this one, like number 21. This is fall 17. So you'll recognize these, and they're all dealing with this equation. The stress, F over A, is equal to the Young's modulus times delta L over L. The stress is equal to the Young's modulus times the strain. And it's really just picking out the numbers from the equation. The force here is 100 newtons. The area of that, in this case is a tendon, is 7.5 times 10 to the minus 5. The Young's modulus, I give it to you here, but again, it'll be on the equation sheet, is 2 times 10 to the 7th. And then delta L, that's what I'm looking for, by how much does it stretch. And then, what was the original length? The original length of this tendon is 0.10 meters, 10 centimeters. And then I solve for delta L. So I don't know what that is.
So these types of problems will be straightforward like this.
Yes, nothing tricky. But any problem is tricky if you don't know how to do it. But it will look like this. It might not be a tendon. It could be, a bar of aluminum or it could be really any number of things. Yep. And you'll have that full sheet that includes the tables and all the equations from every chapter. You get equation sheets for next semester too. Do you know that? Whoop, whoop. Yeah, for the final. Just the one, you don't get equation sheets for all semester, but you get them for this one. By the way, on the final, you will have free response on the final. You'll have one. Don't roll your eyes. You'll have one from every exam. One question from every exam. Am I going to tell you what they are?
Yes.
I'm not going to tell you. They'll be the same, not the same numbers. Yeah, they'll be exactly the same. All they're going to change is the numbers so that you'll get a different answer. Exactly the same. Probably just change one number just to change the answer. Okay? So if you just know those exact free response questions, that'll be 8 questions from the exam. And your exam is usually around 50 questions total. You get 2 hours. Okay? Hold on, how many get? I don't know.
And you put it on the website.
Uh-huh.
Response on there?
Yeah,
Oh, you say not
that's because y'all are the first ones that I've done for. I know, aren't you? I used to do these online quizzes, and they were a waste of time. But this way, okay.
Yeah.
Okay. If I don't have anybody else, okay?
I just like